Mass number. Protons and neutrons are found in the nucleus of an atom and are called nucleons. The sum of protons and neutrons in one atom of an element is called the mass number or nucleon number or atomic mass. This number is actually taken as the mass of the atom since the mass of the electron is negligible. Thus, number of protons plus number of neutrons equals mass number. For example, 1. Hydrogen has 1 proton and 0 neutrons. Therefore, its atomic number is 1, and mass number is 1 plus 0 equals 1. 2. Boron has 5 protons and 6 neutrons. Its atomic number is 5, and mass number is 5 plus 6 equals 11. 3. Nitrogen has 7 protons and 7 neutrons. Its atomic number is 7, and mass number is 7 plus 7 equals 14. It is also possible to calculate the number of neutrons and electrons of an atom if its mass number and atomic number are given. Nuclide notation. Atoms of different elements can be represented by chemical symbols that indicate their respective atomic numbers and mass numbers. Using an arbitrary element X, the mass number A is placed on its upper left end, while its atomic number Z is placed on the lower left end. Thus, element X is represented as X, mass number A, atomic number Z. This is known as the nuclide notation. The following are examples of nuclide representations of different atoms. 1. Hydrogen, mass number 1, atomic number 1. 2. Boron, mass number 11, atomic number 5. 3. Nitrogen, mass number 14, atomic number 7. 4. Oxygen, mass number 16, atomic number 8. With this information, it is possible to determine the number of neutrons and electrons in the atom and write the electronic configuration. For example, in the oxygen atom, the mass number is 16 and the atomic number is 8. Therefore, the number of electrons is 8 and the number of neutrons is 16 minus 8 equals 8. The nucleus of the oxygen atom can therefore be represented as shown in the figure displayed. Isotopes. Atoms of the same element have the same number of protons. However, the number of neutrons in the atoms of the same element may vary. This means that the atomic number of an element does not change, but its mass number can. Such atoms of an element are called isotopes. Isotopes are atoms of the same element with the same number of protons but a different number of neutrons. The existence of such an element is called isotopy. Isotopy is the existence of atoms of the same element having the same atomic number but different mass numbers. It is also possible to get the number of subatomic particles in a given isotope. Many naturally occurring elements usually exhibit isotopy. The most abundant isotope of an element is taken to be the representative of that element. This abundance is usually expressed as a percentage. Examples of common elements that display isotopy are hydrogen, oxygen, carbon, chlorine, nitrogen, and neon. Applications of isotopes. Isotopes are special forms of elements that can be used in various areas, including research, medicine, industry, and agriculture. Some isotopes are radioactive. Radioactive isotopes are special types of atoms that give off energy called radiation. Even though the emitted radiations are dangerous if not handled properly, these isotopes are very useful in many ways. Scientists use these isotopes in various applications, including determining the age of ancient objects using carbon-14, treating diseases in hospitals, tracking how plants absorb nutrients in the soil, and producing electricity for everyday users. Carbon dating, finding the age of ancient items. Scientists use carbon-14 to determine the age of ancient objects. Carbon-14 is a radioactive isotope of carbon that slowly breaks down over time. When a plant or animal dies, it stops taking in carbon-14 from the air. Scientists measure how much carbon-14 is left in bones, wood, or fossils to estimate the number of years that have passed since the organism died. Carbon dating helps archaeologists and historians learn about the past, including the age of ancient human tools, animal fossils, and historical items. Tracers in medicine, industry, and agriculture. Some radioactive isotopes are used as tracers that help scientists track movements or processes inside the body, in the environment, or in industrial systems. A. Medicine. Diagnosing and treating diseases. Iodine 131 is used in hospitals to check how the thyroid gland works. When a small dose of iodine 131 is administered to a patient, the radiation emitted by the iodine helps to create images of the thyroid. Special machines detect the radiation to help diagnose thyroid problems. The radiation also helps to shrink or destroy damaged thyroid cells, leading to the treatment of thyroid-related diseases. B. Agriculture. Studying how plants absorb nutrients. Phosphorus 32 is used to track how plants take in nutrients from the soil. Scientists use it to improve fertilizers and help farmers grow healthier crops. C. Industrial and environmental applications. Some isotopes, such as tritium-3, tracks how water moves underground. This allows scientists to understand the sources of drinking water. Chlorine isotopes are used to study the movements of chlorine in water sources, such as rivers, lakes, and underground water. Sodium-24 is used to detect leaks in underground pipes. This isotope is made artificially. Relative atomic mass. An atom is very small, and it would be difficult to measure its actual mass. To overcome this difficulty, chemists developed a simpler way to express the mass of an atom. This involved expressing the mass of an atom in relation to a chosen standard atomic mass. The carbon atom was chosen as the standard atom, that is, reference atom, and its mass was arbitrarily chosen as 12 units, that is, not the actual value. Then, using an instrument called a mass spectrometer, all the other atoms were compared to this standard atom. This reference is called the carbon-12 scale. For example, it was found that A. Magnesium atom was twice as heavy as the reference atom, so its mass was put at 24. B. Hydrogen atom was 1 out of 12 as heavy as the reference atom, so its mass was put at 1. C. Helium atom was 1 over 3 as heavy as the reference atom, so its mass was put at 4. The mass of an atom obtained by comparing it with the arbitrary mass of a carbon-12 atom is called its relative atomic mass, that is RAM or AR. The relative atomic mass of an element is the average mass of one atom of the element relative to 1 over 12th the mass of one atom of carbon-12. Therefore, RAM may not necessarily be a whole number. That is, AR equals average mass of atom of an element over 1/12 the mass of carbon-12 atom. The following gives the atomic numbers and relative atomic masses of the first 20 elements in the periodic table. The relative atomic masses of such elements are obtained by calculating the average mass of all the isotopes of each element. For isotopic elements, The relative atomic mass, that is the RAM, can be calculated using the following formula. Relative atomic mass, that is RAM, equals the summation of isotopic mass times percentage abundance.